Okay. Okay, so yeah, this is going to be more of a short format presentation, just to have more time for discussion if it's needed. So it's going to be about the private transactions life cycle, specifically about the simulation of the call graph that can be generated by sending a private transaction. So yeah, we are going to use some simple example contract, but will be useful to visualize this. So as you know, these private secret functions can call other external functions in other contracts, or might be in the same contract. It doesn't really matter for this case. So you can have multiple levels of nesting. You can be calling one function, but it will call two more, which in turn will call another, etc. So, but a user, when trying to send a transaction, is going to trigger the transaction against an entry point. The same as in Ethereum, you send a transaction to a specific contract with some data that selects a function, but that smart contract can trigger multiple messages, are called in Ethereum. Multiple messages in the life cycle of the transaction. So we have these three contracts as an example. So the user is going to interact with the top level one, which we'll call B and C in the middle one, and the middle one in the B function we'll call the D one. So we are two levels deep. So this contract is going to get compiled to an API, okay? The top level one, that is the one that the user is going to interact with. So for example, this is an example API of a contract. It's going to have a list of functions, but the function that we actually care about in this one, that is the one that the user is going to interact with, is the function A in the top level contract. And some data that we have that we can have about the functions in the API would be the name, whether it's secret function or not. Right now we are only dealing with private functions, secret functions. So this is going to be a private one. If it's a constructor or not, the list of parameters, but for simplicity, we are not going to have parameters or return types. But also in the API, we need to have the bytecode, the ASIR bytecode, and as a well, for simplicity, basically for efficiency, we can have the verification key along with the bytecode, but we could generate the verification key from the bytecode, no problem. So, but this is this makes it simpler to prove execution if you already have the VK. Okay, so this would be the API for the top level one. So how is this going to be used? So we are going to have some example dApp that is going to create a new contract class. This contract class will get the API and will generate like these stub methods, similar as in Ethereum. You auto-generate a method A for the function A that accepts the same parameters and takes the parameters and the knowledge that is in the API and converts it to the correct types, same as you have in Web3 or Ethers, JS, etc. for Ethereum. You need to provide also some deployment details in this case, because we are not deploying a contract. We're calling the function A that is from a specific instance. The deployment details, I suppose that is going to be only the address of the contract, but I don't know if we need also the portal address to reconstruct the contract leaf. By the way, if at any point I want this to be more of a discussion, but so you can stop, you can ask, you can discuss whatever, or else at the end we can discuss some points. Yeah, so you will, the dApp will create this contract abstraction and it will call the function A. So it will generate a transaction request. The transaction request is going to have these arguments encoded, but in this case, we have no arguments. So it's going to have just details, metadata about what we are calling. We are calling this contract in this address, this function, some metadata about it. That is not that relevant for this presentation. So we are going to ask the Aztec RPC server to simulate it and then sign it and etc. But in this case, we want to simulate it. So two important pieces of this in the Aztec RPC server are the simulator itself and also the private DB. And why is the private DB important for this simulation? Well, the private DB not only has all the private nodes or the some keys but also it has to have the ASIR, the bytecode of some known contracts. It has to cache to have verified and stored the bytecode of some contracts, and you are going to see why in the next slide. So, what do we need when we simulate the transaction? What do we need to know about the transaction? So, first, we need to figure out the execution graph. What is going to call this function? Okay. So in this case, the execution graph will be A will call B, which will call D, and then after that is solved, A would call C, as you see here in this graph. So since we are going to have this execution graph, but we only have the bytecode of the function A, we need to have in this private DB some data about these other contracts that the function is interacting with, the middle and the inner ones, and also about the functions themselves. So what data we need? We need to know the ASIR of the B, C, and D functions, which the user has not provided with the ABI of the top level contract. But also we need to have some data to be able to generate hash paths, witnesses about the function being a part of the contract leaf, where is the contract leaf, etc. Some data about these contracts that we have to cache, to store, including the ASIR of the inner functions, the functions deep in the call tree or graph. So what do we need to solve now that we have all this data? We know the graph, we have the ASIR of all the functions. So what really does the user need from the simulation? So basically it needs to check if the function succeeds and also what it's going to do. It's going to consume some nodes, it's going to create some nodes. So for this, we can basically generate the intermediate witness. The intermediate witness, generating it is what is done right now for Noir circuits. So when you generate the intermediate witness, you, for example, would generate the return values in a Noir circuit, if I'm not mistaken. So and other things such as directives, etc. But yeah, so this would allow generating the intermediate witness to check if the function succeeds, and also this intermediate witness is needed for the prover and includes the public inputs that is going to be needed for the kernel circuit, that in this case is the verifier of these functions. So we can generate the intermediate witnesses and the pre-images. These pre-images metadata about the execution. For example, in the intermediate witness, you are going to have I created a new node with this commitment, but you need to know the pre-image of that node to be able to use it later. So metadata about this that is not in the witness, but that you will need to store if you actually want to execute this call. Yeah.
So could you go over again how to generate this intermediate witness?
Yeah, so right now the ACVM, that is a module of the Noir team, has a partial witness generation, is called, or intermediate witness generation. And what it does is it takes all the opcodes and basically tries to figure out all the missing data in the witness, if I'm not mistaken. I'm not an expert in Noir at all, but if you have a constraint that is only missing one variable, then you can figure it out with the others. Right? And for directives, for example, you can pre-calculate the inverse of one number and put it in the witness, and that will be part of this intermediate witness generation. It will also need some constraining, but it would be part of this. So, or if you have, for example, the return value, you can figure out the return value by applying all the constraints of the circuit, and that would be included in the witness. But I'm not an expert in Noir. It's just my rough understanding. So what we need is this intermediate witness that includes all the that will include the public inputs and the pre-images. So how can we do it? So one proposal would be to extend this intermediate witness generation of the ACVM to extend it to support the features that Aztec 3 needs. And which is the main one that Aztec 3 bytecode needs would be loading data from outside the simulation itself. So right now, in the intermediate witness generation, you don't need to talk to anybody. If you want to know the inverse of a number, the ACVM can solve that. Just do it in Rust. But now, for example, if you have some opcode that could be a directive, like for example, load some nodes, you will need to communicate with the caller, with in this case would be the Aztec RPC server, for it to provide some nodes or some secret or to call another function. So the idea would be to have this separation where you will have this extension of the ACVM, this Aztec 3 VM, that would, given a bytecode, the bytecode of one function and the arguments, would solve the partial witness and the pre-images with some callbacks for solving these special directives, these directives that need nodes, that need secrets, that need some external calls. This is a proposal, this is what I have in my mind, but we can discuss this later for sure at the end, or right now if you want. So one point that can be a little bit complicated is how are we going to solve the nested calls? Because if this is only solving it for one function and we have this callback for nested calls. So one proposal that I wanted to discuss is basically doing this. That will be spinning multiple ACVMs for when you need to solve nested calls. In this case, for example, that B called D, you would be, well, A called B, for example, that is this simpler case. So the simulator would fetch the ASIR of the function A, no problem, we have it available. It would start the simulation of function A, and the function A would at some point need to call the function B, as we saw previously. So the simulator would fetch the ASIR of the function B, and then it would spin another ACVM just to solve this function call, and this could be all the levels deep that is necessary. I wanted to discuss this because I don't know how feasible it is with the WASM ACVM to have this multiple execution context, maybe have multiple virtual machines. I don't know if the memory requirements are too high or is unfeasible for any other reason. So what you would do is you would accumulate these nested execution contexts. So what will be the result of all this? So you are able to solve one function and provide callbacks to solve all the nested calls. And what you will have at the end would be something like this, where for one function, you will have a context with the public inputs that will be extracted from the partial witness. So in reality, this is just an extraction from the partial witness. You will have the pre-images, and you will have also an array of nested context that is a self-reference. So how would this graph be? It would represent exactly what we saw previously, this small graph. So you will have the execution context for A that has two nested execution contexts that would be B and C, and B has one nested execution context that would be D. So it would be this graph, but in this structure, in this recursive structure. This is just as documentation, the structure of the public inputs. This is taken from the Miro board. Okay, so you will have all the partial witnesses solved, and you will have this structure, this graph. So if you weren't able to generate the partial witness, then the simulation is, some constraint is not met, something is not solvable, so the simulation has failed. The same as right now in Noir. If you try to do the partial witness generation and you don't fulfill the requirements, the constraints. So what can we do with the simulation result with this execution context structure that is nested? So now it can be used to prove the execution of these four, in this case, in this example, there is 4 function calls. So it would be one proof per function call. And in order to prove it, you need the ASIR of the function and the partial witness. And with that, you can generate the proof. And one thing that I also wanted to discuss is who is going to do this ASIR to proving key transformation, who is going to have this knowledge. Because right now, for example, in Noir, I think that it is the ASIR backend, it's called Aztec backend, I think it's called, that has this knowledge of how to convert the ASIR to a simple constraint representations that then Barrettenberg can use. So It's going to be Noir.js as a preprocessor, like is the Aztec backend doing now, or it's going to be just directly circuits.js is going to understand us here. It's something that we can discuss at the end. So just to wrap, when we have this nested function execution context, this structure, this graph, we can run it through the private kernel. That will be the end to generate the final proof. So all the function calls, the 4 function calls have been proven previously. So you will run the private kernel as many times as function calls that you have. So in this case, you will start with the function a, that is the root of the tree. You will start with the function a. So the stack items will include, among other things, this is a simplification, but would include the public inputs. That includes the hashes, as you see here, of the private call stack. And it will also include the private function proof that we have generated in the previous step. So in the first execution, you will have A as the previous stack, and it will verify that the new stack that contains B and C corresponds with the private call stack of the public inputs of A. Then it will pop B in the second iteration and will push D, that is the function that is called by B, and then it will be popping until the stack is empty. So when you have, well, this hides the details about the specific function calls, because if you see here in the public inputs, there is a lot of metadata about what the function is doing, and we don't want that. So since you have all this metadata, the private kernel is going to have these public inputs as a private input, which is a mouthful, but it's going to be a private input to the private kernel. So since it's a private input, it's going to hide all this metadata about which functions we are calling actually. So we preserve the privacy. And finally, when you have popped all the structure, all the items of the tree, and all the stack is and the new stack is empty, you have the last iteration of the private kernel. And this is my understanding of how the private kernel would work, because I'm also not an expert in this part. But it's my understanding of how the simulator output will be used along with the proofs. Okay, so yeah, this was mainly the presentation, and I written some points to discuss to see if people had some ideas, some stuff about this. That would be these ones. So if someone wants to discuss something about this, about for example, this separation between simulator and ACVM, having these callbacks to the TypeScript context and spinning out instances of the ACVM. I don't know how feasible it is, or if it was what you guys were thinking, if it fits with your idea, for example.
I think that should be compatible with the interface I'm compiling to, unless there are any hidden gotchas with WAS and bindgen not liking multiple entries into the same async function. But I guess we'll discover that soon enough.
Yeah. Yeah, I one thing that I didn't touch that is related with the next point is something that we discussed on Friday about this, how to run the unconstrained functions. Because on Friday, we were discussing like, yeah, if the unconstrained functions are JavaScript, we can, okay, like Oracle calls, fetching some data, these callbacks, in the end can be done as an unconstrained function, because it's basically that. So you could just send JavaScript over to the caller and say, hey, evaluate this for me, including fetching data from the private DB or whatever. But the problem with that, I was discussing that with Leila after the meeting, is that that will be very, apart from the problems from developer experience, because you have to write in JS your unconstrained functions instead of Noir, it would be very, very difficult to run that in a secure manner. Isolating JavaScript code in a JavaScript environment can be done. You can do it with web workers, you can do it with a lot of stuff, but in reality, this could be quite dangerous. If a contract developer can write unconstrained functions in JavaScript and have it evaluated,
That's a very good point. And given the context of what programmers people be writing in Noir, I do think that's a very big concern. I mean, for example, imagine if your Solidity contract could inject JavaScript code into into your DApps execution environment, into your DApps runtime. That would be pretty bad. So what was the consensus then? Like, what's the current consensus around JavaScript versus writing unconstrained functions in Noir?
I don't know, because we were discussing last Friday. I don't know if it has advanced a little bit.
So what was the consensus on Friday?
I felt like it was like Noir was the desired language, but it could be. But I think that it was a point made that it could be complicated, because you will have to spin like individual virtual machines for the unconstrained functions in Noir internally. Correct me if I'm wrong, because it's a little on top of me.
Yes, but probably just one VM, right? Because the execution is serial in Noir. But
the thing is that with Noir you compile to opcodes that relate, if I'm not mistaken.
Yeah. So you need some kind of execution context. So like
you need like a fake witness to operate in, kinda, more or less.
I see.
Yeah. So we were talking on Friday in this talk that it would be simpler in JS, but I think for production it would be very, very easy to be. It would be very easy to be a problem. It would be very difficult to properly isolate in all environments, in Node, in the browser, in everywhere.
Yeah, good shout out, Leila, for pointing that out.
I think for Aztec 3 specifically, like what we need to implement as unconstrained functions for Aztec 3, it is fine because we can write the JavaScript directly part of Aztec.js, so it will be like hard-coded by us. So I think it is fine for what we need for Aztec 3. But when we want to provide this functionality, like of unconstrained functions to smart contract developers, so they can write their own, then this is a problem if they can inject JavaScript.
Yeah.
But I don't think there is a solution. So either they have something powerful and then they can do something that is really unsafe for you, or it's restricted and then it's not powerful. So I don't think there is a solution here.
I think there is a solution. It's just you can create something which is powerful in the context of something that's Turing complete, but just you need a very clear separation of runtime environments. So I don't quite see. I do appreciate it would be slightly more complex, but I don't see the fundamental problem with writing on the constrained functions in Noir. You might need a slightly additional syntax, but like as in, you know, like if assuming Noir is functionally Turing complete.
Well, it really depends what you want to allow. Like if it is just writing a Turing complete language, and then yes, that's easy. But if you want your language to be able to access internet, like call a web API to get the weather for your store you want to do, then it will be unsafe for sure.
I see what you're saying.
Yeah, in the end, what we want is like a limited virtual machine for these unconstrained functions, something like that. Like the ACVM could be a. I think you're mute, unless I run out of battery.
So yeah, for Aztec 3, you need to access some database.
Yeah, but those could be implemented as. For example, this database could be implemented as specific directives. For example, that was my natural response of how this could be done, and I might be completely wrong because not an expert at all. But for example, the specific Aztec 3 unconstrained piece of code that are fixed by Aztec 3 could be written as specific directives, like load nodes, and these are a directive to load an unlimited number of nodes, and then you have unconstrained pure functions that are executed within the ACVM to reduce those nodes, for example, or whatever. But like I think I had an example here. This might be completely unfeasible, but that you have in the bytecode at some point these directives that are the ones that do the Oracle calls the database access, and that for unconstrained user-facing and unconstrained functions, you just do pure functions, like no data outside the arguments.
So I mean, you raise an interesting point because it's not something I really considered. I guess what you're describing really is like basically the ability to like have Oracle, like basically to implement oracles directly inside a NOR contract. So if you want your own, as you said, like you want to ping some random server to get some information, you could, in theory, do that directly from the NOR contract if you could inject JavaScript. I guess.
But do we want that?
I mean, it's powerful. I wasn't assuming we wanted that to start with, at least for V1. Yeah, I think that's something that we can probably well, my gut feeling is something that we can address in the future, like once Aztec is kind of released and as an active developer ecosystem, as in if you want Oracle access to things like external website servers, etc., you can always program them at the app level, and
have it as arguments in the end.
Yeah, exactly. Which makes it obviously the DevX for those particular applications is worse, but I think we need to prioritize security, unfortunately. Well, I mean, unfortunately, in terms of like features, because yeah, like I feel like we're putting a big target on our back if we allow for JavaScript injections into NOR contracts. It's just yeah. Yeah, I feel like there's concerns around security. We should follow the we should take the secure path. This is my gut feeling on this.
Lassie was talking in the comments about how would the unconstrained functions work in a public function, and I assume that they want like that in the end these unconstrained functions that are for Oracle fetches like load nodes, etc., are only, I assume, for private functions because it's the only ones that have real access to the secrets. Or
yeah, I'm not sure we would need unconstrained functions in the public functions because the only state you can access is the public state tree, which I don't think needs.
From the earlier like diagrams at least, the public function can both access the public state but also the private state, because you could have a case where you want to insert something in the append-only tree, depending on, say you want to move something from public domain to private domain.
Yeah, good point. Yes.
But could that be passed as arguments to the public function and checking the caller? Like if it's the same contract, it's myself that is calling me. I'm a public function. I don't know.
It was more that if it's a public function, the sequencer will execute it, so it needs to be available. And if we have, say we have JavaScript, whatever, then it might end up being like a very large like code base that you have for the unconstrained or whatever, or something like that.
It's more than that, actually. It's the fact that you simply can't have unconstrained functions in a public function because the purpose of an unconstrained function is supposed to act as it's supposed to be a guide, basically, to figure. It's a program that describes how to create the correct witness assignments to the constraints that the NOR program is creating. But you don't know that that's the case. As in, for a private function, you can assume that's the case because if it isn't, then the user can't make a valid transaction. But for a public function, which the sequencer is executing, they cannot trust a directive to be honest. Therefore, you cannot have directives in public functions. Because the following the directive may lead the sequencer to create a fake of an invalid proof, and then they don't get paid for their work, I think.
So it has to be. I don't remember the word exactly. Like all the witness has to be predictable.
Yes, derivable. I think maybe we need to chat about this a bit more next week, because I think might affect the design of public functions in the public VM, because
Complicated.
yes, that is something that basically a serial case, they're not like regular opcodes in a low level language, in that they're not deterministic, as in they can have more than one degree of freedom, and that is a problem for public functions.
Well, if they are properly constrained, the result, I'm not sure it's a problem.
The problem is, no, it's not about being properly constrained. The problem is every noir opcode must only have, in a public function, must only have one degree of freedom, as in everything must be derivable by the sequencer. They must have enough information to derive everything. If that makes any sense. Maybe I'm. Yeah, I don't have enough. I think sorry, my brain is Swiss cheese at the moment. There are two problems with public functions. One of them is giving the sequencer enough information to make the proof. The other one is making sure that the sequencer has faithfully provided the correct witness assignment, and has not chosen to create an invalid proof in the presence of good data. And I feel like the non-determinism in opcodes could cause a problem with the latter. Does that make any sense, Guillaume?
Well, yes or no. I mean, like for me, what you just explained is a feeling. So maybe it's correct, but maybe it's not. So I'm not sure.
Zach, do you have an example of how that would be a problem? Maybe that would be helpful.
So let's say that I am okay. So you got an opcode to do Pedersen hash, right? Where so you have an opcode to do Pedersen hash. So the idea is what you have is you have your inputs, and then a bunch of constraints are created to like what the prover does is they provide. What you're doing is you're doing basically elliptic curve multiplication. So you're multiplying a point by a scalar, and at every step you're providing the results of your of an elliptic curve point additions. What if the sequencer just decides to create invalid witnesses there? They actually if the x coordinate is supposed to be 5, they place 3, and the proof fails. And so the transaction sender has done nothing wrong. Their transaction should be valid, but the sequencer has, through malice, chosen to make their transaction fail. The difficulty when executing public functions is you need to be able to tell the difference between two things. You need to tell the difference between when the proof is invalid because the transaction execution logic has thrown an error, and the case where proof is invalid because incorrect values have been assigned to wires in your gates. You need to make the distinction between those two, because the former is caused by the transaction sender giving the sequencer bad data, and the latter is caused by the sequencer not doing their job properly. And if you can't tell the difference between the two, then you can basically sequencers can launch censorship and griefing attacks by basically making transactions fail when they shouldn't.
But then what you need is a virtual machine, right? That is
You do need a virtual machine. That's what we were going to do. But my plan was to make the virtual machine evaluate NOR opcodes, and I'm starting to wonder if that may be insufficient.
Why is the user signature not sufficient to check against the witness that's been generated? Because the signature's over an intent.
The user doesn't generate the witness.
Cannot know the data for the witness.
When a sequence is constructing a proof of a public function call, they're generating that proof, right? Like this is after the user has sent that transaction. None of the information that's encoded in the witness assignments. We're talking about tens of hundreds of megabytes of information here. That's derived from state that's derived possibly from state reads and state accesses that the transaction setter does not have access to.
Yeah, because it cannot know, for example, the order of the transactions, so that could affect. This you don't know the state of the system when that public function is going to be executed. It feels a little bit to me like the in the Ethereum transactions when you basically have a valid transaction but status failed. So it's like it's asking for having a level of indirection, but if
I think it might be okay. I mean, it depends on the structure of the virtual machine, because the virtual machine basically has to ensure that when executing complex NOR opcodes, the whole point of it, the point of a virtual machine is that you can create a system where a valid transaction must have satisfiable witnesses. As in, if the sequencer chooses to create invalid witness assignments, the proof is invalid, but therefore that means that proof cannot be put in the roller block. You want to run a VM so that faithfully executing the user's instructions does not result in a failed proof. It results in a valid proof where the output of the VM is 0. So maybe I'm just running around in circles here, and maybe it's not a problem. It depends on the specific structure of the ACVM codes, but maybe it's not a problem. Yeah, going back to directives. As in,
like I cannot think of an example where you need a directive in a public function. Like, what do you want to load? What information do you need that is not from the inputs of that public function?
Yeah, I'm hopeful we don't need directives in public functions. And I don't think you can have directives in public functions. Going back to why, it's what are directives used for? Directives are used to basically assign witness values, Y values, to gates in your circuit. Ultimately, that's what happens from a directive. But in the public function model, invalid Y values create they don't create failed transactions they don't create transactions that revert that you can include in a roll block. They create transactions where the proof is invalid and therefore they can't be included. Therefore, basically, in a public function call, if the resulting proof is invalid, the sequencer has wasted their work. They won't get paid. And so if the contract contains a directive that deliberately assigns unsatisfiable witnesses to wires in the NOR circuit, then that basically turns out to a griefing attack, because you're then instructing the sequencer to spend all this work generating a proof for a transaction that is invalid, and therefore they cannot get paid for. Does that make any sense?
And it's kind of the other way around. Not much the sequencer wanted to create invalid proofs to censor someone, but also points to a VM.
Yeah. Okay, so yeah, I think basically we probably can't have directives in public functions, which means that, well, you can't read from the private state tree in a public function, but you never could anyways without leaking secrets. I think you should still be able to write to it's a private state tree, but you should still be able to write to a private state tree in a public function, because that shouldn't require directives to create a note from scratch, I think.
But everything you write is going to be public.
Yeah. So
which maybe
you probably shouldn't, but it's important to have the option there, because, for example, Aztec Connect, in our DeFi bridge, we effectively are writing to, like, if we were to turn that into an Aztec 3 set of contracts, there is a part where we're writing to the private state tree in a public function. That's when you're kind of completing a DeFi claim note. The idea is that in a private function, a user generates a DeFi claim note, but then in a later public function, the rollup provider takes that note and adds on what is like a DeFi interaction nonce, adds that into the note, and then adds it into the private state tree. And
does that mean the claim note would need to be a public state? Like if you just go for the Aztec
No. It means the claim note would the partial claim note would be a parameter, input parameter to a public function. That public function would then complete the claim note and add it to private state.
The step before though, when you go from like a deposit, like a DeFi deposit, like that's read by something, isn't it?
Could you clarify what you mean there?
So like in to get to a point where you can actually send funds to a DeFi protocol, like before you have the claim note, you create this partial claim note.
That's what I'm talking. No state. The user creates as a private function which computes a partial claim note. Then that then gets like that becomes the input parameter to a public function call, and then the public function will write to the private state tree.
Makes sense. Okay. Yep.
So I think we are running out of time. So thank you for the discussion. I think we have clarified some points that are important for this part of the prep functions. So thanks.